Hi friends, we have studied how to analyze networks for finding voltage across, current flowing through or power dissipated in each components of the whole network. For that we used Ohm's law, KCL, KVL, mesh and nodal analysis etc. But in many practical applications it is not necessary to find out the value of voltage across, current flowing and power in every components. We will be required to find out the values only in a particular component. In such cases, we can make use of this network theorems. In the following classes, we will be discussing some of the network theorems. Some of network theorems we are discussing will be Thevenin's theorem, Norton's theorem, superposition theorem, maximum power transfer theorem, etc. Thevenin's theorem. Thevenin's theorem states that any two-terminal active network can be replaced by an equivalent circuit consisting of a voltage source VTH, that is V Thevenin, and a series resistor RTH, that is R Thevenin. In this circuit, see, in addition to the load resistance, there is a voltage source and three resistances. As per Thevenin's theorem, this much can be simplified into just a voltage source VTH and a series resistance RTH. Even if how complex this circuit is, we can simplify this thing to equivalent Thevenin's circuit. Steps for finding Thevenin's voltage VTH and Thevenin's resistor RTH. For finding VTH and RTH, first we have to remove that load resistance from the network. So here the load resistance is here, we have removed it. So the balance circuit remaining is this much. Next we will find out the Thevenin equivalent resistance RTH. For that, what we have to do is, we have to short circuit whatever voltage sources are there in the circuit, and if any current sources are there, that we have to open circuit. Then in this case, this will become like this, because here only one voltage source is there, that is short circuited. Then we have to calculate the resistance between A and B, which is RTH. Here R1 and R2 are in parallel, which is in series with R3, that is R1 and R2 is in parallel means the effective resistance is R1 R2 divided by R1 plus R2 plus the series resistance R3. So RTH is equal to R1 R2 divided by R1 plus R2 plus the series resistance R3. This is the Thevenin's equivalent resistance. Next, Thevenin's equivalent voltage is to be found out. See in this figure, we have already removed that load resistance. So the voltage coming across A and B is VTH, which is the Thevenin's equivalent voltage. See, the voltage across AB is the same as the voltage across R2, as here it is open circuited and no current is flowing through R3. For finding voltage across R2 or current through R2, we can use any method such as Ohm's law, voltage divider method, KVL, KCL, mesh or nodal analysis. Here R1 and R2 are in series, so voltage across R2 is equal to this V into R2 divided by R1 plus R2, which is equal to VTH. Therefore, we can draw the Thevenin equivalent network as the VTH we found out here and this RTH which is in series, which we found here. So our given network is simplified as a Thevenin voltage VTH in series with RTH. Here RTH and RL are in series. The same current IL is flowing through RTH and RL. Therefore, load current IL is equal to VTH divided by sum of these two resistances RTH plus RL. Now, the voltage coming across load resistance is current into resistance IL into RL. In this example, we are asked to find the current through 2 ohm resistor in this figure. See, here we will apply Thevenin's rule. For finding Thevenin's equivalent circuit, first we have to remove this load current. Now, our figure becomes like this. See, 2 ohm is the load current and that is removed. Next, from this circuit, to find out Thevenin's equivalent resistance, we have to short circuit all the voltage sources and open circuit all current sources. In this case, there is no current sources. So here the voltage sources are this 40 volt, 20 volt, 10 volt, which we have to short circuit. Then this figure becomes like this. See here these two voltages are shorted. Then in this branch only 5 ohm is there. Here this 10 ohm is there, and this 10 volt is also shorted. So looking from here, between terminals A and B is the Thevenin's resistance. In this circuit, as this 5 ohm and 10 ohm are in parallel, RTH will become RTH is equal to that 5 ohm in parallel with 10 ohm. That is equal to 5 into 10 divided by 5 plus 10. That is 50 divided by 15, which is equal to 3.33 ohm. So RTH we got as 3.33 ohm. Next, Thevenin's equivalent voltage VTH is to be found out. We have to remove this load resistance, and the voltage coming across this opened terminals A and B is the V Thevenin. That is Thevenin equivalent voltage VTH. See, in this mesh, let the current flowing is I. Then applying KVL for this mesh, applying KVL, as the direction of current is in this way, here in this resistance voltage drop is there, here also voltage drop is there, where current entering is plus and leaving is minus. In this resistance also current entering is plus and leaving is minus. Applying KVL to this mesh, see in this 40 volt there is rise in potential, so it is plus 40. Then in this 5 ohm, so the fall in potential is I into R, 5 into I. As it is fall in potential, it is minus 5 into I. Then here positive to negative, so that is minus 20. Then in this resistance also positive to negative, that is voltage drop is there, minus 10 into I, which is equal to 0. Simplifying this equation, we will get 15I is equal to 20. Therefore, I is equal to 20 divided by 15, which is equal to 1.33 ampere. In this mesh, here VTH is coming. Writing VTH equation for this mesh, here plus this VTH is positive to negative, that is fall in potential minus VTH. Then here it is rise in potential plus 10. Then here it is minus 2 plus, so plus 10 into I is equal to 0. The value of this I we have found as 1.33. Substituting it here, this equation becomes minus VTH plus 10 plus 1.33 into this 10, that is 13.3 is equal to 0. Therefore, VTH is equal to 10 plus this 13.3, that is 23.3 volt, and RTH we have found as 3.33 ohm. VTH we got 23.3 volt and RTH we found as 3.33 volt. So our Thevenin equivalent circuit becomes RTH we found as 3.33 ohm and this VTH is 23.3 volt. The load resistance already is given as 2 ohm. See, as this RTH 3.3 ohm and load resistance 2 are in series, that can be added. The total resistance becomes 3.33 plus 2 ohm. Therefore, total resistance which are in series is equal to 3.33 plus 2, which is equal to 5.33 ohm. Therefore, load current, that is the current through RL, is equal to this VTH divided by the total resistance. As both are in series, the same current will be flowing, is equal to 23.3 divided by this 5.33, which is equal to 4.38 ampere. In the circuit shown in figure, we have to find the current through this 2 ohm resistance, which is connected between the two terminals A and B. To simplify the circuit, we will use Thevenin's theorem. For applying Thevenin's theorem, first we will remove the load resistance 2 ohm. Next, to find out Thevenin's equivalent resistance, we have to short circuit all voltage sources and open circuit all current sources. In this case, two voltage sources are there which we will short circuit, and as there is no current source, no question of opening it. After shorting this 2 volt voltage source and 4 volt voltage source, the circuit will become like this. Between A and B is the Thevenin's equivalent resistance. Therefore, Thevenin's equivalent resistance can be found out as here this 2 ohm and 12 ohm are in parallel. 2 ohm is in parallel with 12 ohm. This is coming in series with 1 ohm. So we will add this parallel connected 2 ohm and 12 ohm to 1 ohm which is in series. These 3 resistances are coming in parallel with 3 ohm. So this is coming in parallel with 3 ohm. Simplifying this by 2 and 12, which are using the formula 2 into 12 divided by 2 plus 12 for this parallel connection, plus 1 which is in series, and the result will be in parallel with 3 ohms. So this is equal to 1.43 ohm. This is the Thevenin's equivalent resistance RTH. Next, Thevenin's equivalent voltage VTH is to be found out. In this circuit, 2 meshes are there. This is 1, and here after opening this load resistance, these and these 2 combined together becomes mesh 2. Let this is current I1 and this is current I2. Then applying KVL for mesh 1, KVL for mesh 1. So here it is rise in potential, that is plus 2 volt. Then here is, as current is in this direction, it is entering here positive, leaving here negative. Here current is entering here positive, leaving here negative. As current is entering here and leaving here, there is drop in voltage of 2 into I1. So as it is drop in voltage minus 2 I1. So as far as mesh 2 is concerned, I2 is flowing in this way. So in this resistance it is entering here, leaving here, here it is entering here and leaving here, it is entering here and leaving here. So when this 12 is concerned, as this current is going from positive to negative, minus 12, and as we are in mesh 1, I1 is to be written first, minus I2 which is in the opposite direction is equal to 0. Simplifying it, we will get 14 I1 minus 12 I2 is equal to 2. Let this is equation number 1. Apply KVL for mesh 2. In 1 ohm there is a voltage drop of I into R. As it is voltage drop minus 1 into I2. Then here also voltage drop is there, minus 3 into I2. Then as here it is positive to negative, that is fall in potential of 4. Then coming here also positive to negative, that is voltage drop. Therefore minus 12 into, as we are in mesh 2, I2 is to be written first, minus this I1 which is in the opposite direction. This is equal to 0. Simplifying it, we will get minus 12 into I1 plus 16 I2 is equal to minus 4. Let this is equation number 2. Solving equations 1 and 2, we will get I2 is equal to minus 0.4 ampere. As I2 is flowing in this direction where this VTH is containing, VTH equation becomes, so here it is minus 2 plus, that is plus VTH. Here it is in this direction, that is drop in voltage minus 3 into I2, then fall in potential minus 4 is equal to 0. Value of I2 is minus 0.4 ampere. Substituting it here, we will get VTH is equal to 2.8 volt. Therefore, we found out VTH is equal to 2.8 volt and RTH already found out from here, it is 1.43 ohm. Therefore, Thevenin's equivalent circuit can be drawn as VTH we got as 2.8 and RTH is 1.43 ohm. Load resistance RL is equal to 2 ohm. Therefore, IL which is flowing through the series resistances RTH and RL is the same. Therefore, IL is equal to VTH divided by these two resistances which are in series, RTH plus RL, that is equal to, here VTH is 2.8 divided by RTH is 1.43 plus load resistance 2 ohm. This is equal to 0.82 ampere. In this problem, we have to find the Thevenin's equivalent of the network with this 24 ohm as the load resistor. Also, it is asked to find the power dissipated in this load resistor. For applying Thevenin's theorem, first we will remove this load resistance. Next, to find the Thevenin's equivalent resistance, we have to short circuit all voltage sources and open circuit all current sources. In this circuit, no current sources are there, only one voltage source is there, that we have to short circuit, so that our figure becomes like this. See, for convenience, we will bring these two terminals to outside, then it will become as this one. This A came here and B is about here, and this shorting we will draw through the middle point. So here this 30 ohm and 50 ohm are connected, one end here and the other end here. That means 30 ohm and 50 ohm are in parallel. Like this, 20 ohm and 5 ohm are also in parallel, so that this can be further simplified and drawn as like this. See, this 30 and 50 are in parallel, which is in series with 20 and 5 ohm. Therefore, the Thevenin's equivalent resistance, which is between A and B, is RTH is equal to this 30 ohm in parallel with 50 ohm, which is in series with 20 ohm in parallel with 5 ohm. This gives 22.75 ohm. Next, Thevenin equivalent voltage VTH is to be found out. In the circuit, VTH is coming between points A and B. This can be written as, see, this 30 ohm and 50 ohm are in series, and from here this connection to A is going, then VTH from B at this point, this 20 ohm and 5 ohm are meeting. The total current coming from 220 ohm is coming here and split up into I1 and I2, as these two resistors and these two resistors are parallelly connected. Here this I1 is equal to 220 volt divided by 30 plus 50. I1 is equal to 220 divided by 30 plus 50, which is equal to 2.75 ampere, and I2 is equal to 220 divided by 20 plus 5. I2 is equal to 220 divided by 20 plus 5, which is equal to 8.8 ampere. See, in this mesh containing VTH, here is the positive terminal, and we will start from VTH. As VTH is from negative to positive, Thevenin's equation for top loop is, here it is from minus to plus, rise in potential, so plus VTH. Here also minus to plus, so plus voltage is 30 into I1. 30 I1. Here plus to minus, voltage drop is there, so minus 20 into I2. Minus 20 I2. This is equal to 0. Substituting the values of I1 and I2 in this equation, we will get VTH is equal to 93.5 volt. So we got VTH as 93.5 volt and RTH as 22.75 ohm. That is, VTH is 93.5 volt, RTH is 22.75 ohm, and we know that RL is equal to 24 ohm. 24 ohm. As this RTH and RL are in series, the same current IL is flowing through both of them, and the voltage across both these resistance is VTH, that is 93.5. Therefore, IL is equal to 93.5 divided by 22.75 plus 24. This is 2 ampere. Now, power dissipated in this load resistance RL is P is equal to IL square into RL, because P is equal to I squared R. This is equal to 2 square into 24. This is equal to 96 watt. In the circuit, we are asked to find the current through this load resistance. For that, we will apply Thevenin's theorem. For applying Thevenin's theorem, first of all, we have to remove this load resistance. Next, to find the Thevenin's equivalent resistance, we have to short circuit all voltage sources and open circuit all current sources. See, in this figure, here is one current source and here is one voltage source. First, we will short circuit this voltage source. Now we will open circuit this current source, so that figure becomes like this. This 12 ohm in parallel with 6 ohm, and here is the Thevenin equivalent resistance. See, RTH is equal to the 6 ohm in parallel with 12 ohm. This is equal to 12 ohm in parallel with 6 ohm. That is equal to 12 into 6 divided by 12 plus 6, which is equal to 4 ohm. Next, Thevenin's equivalent voltage VTH is to be found out. In this figure, two meshes are there, mesh 1, mesh 2, and let I1 is the current in mesh 1 and I2 is current in mesh 2. As current is flowing in this direction, in this resistance, here it is entering plus and here it is leaving, so minus. While in this mesh, current is entering here plus and leaving here minus. In this resistance, current is entering here plus leaving here minus. But it is already given that the current flowing in mesh 1 is 6 ampere. That is, I1 is equal to 6 ampere. KVL for mesh 2 gives, as I2 is in this direction, in this 42 volt, it is from negative to positive, that is rise in potential, plus 42, then here it is fall in potential, minus 12 into, as we are in mesh 2, I2 is to be written first, minus I1, which is equal to 6 ampere, minus here also fall in potential is there, minus 6 into I2. This is equal to 0. Solving this equation, we will get I2 is equal to 6.33 ampere. This VTH is the same voltage across 6 ohm. That is, VTH is equal to voltage across 6 ohm. That is 6 into this I2, 6.33, which gives 38 volt. So we got VTH is equal to 38 volt, RTH is equal to 4 ohm. This RL is given in the circuit as 3 ohm. Here the load current IL is passing through RTH and RL, which are in series. Therefore, IL is equal to VTH divided by RTH plus RL. That is equal to 38 divided by 4 plus 3, which is equal to 5.43 ampere. In example 5, for the circuit shown, we are asked to determine the current through the load resistance 5 ohm, which is connected across terminals A and B using Thevenin's theorem. For applying Thevenin's theorem, first we will remove the load resistance. Next, to find out Thevenin's equivalent resistance, we have to short circuit all voltage sources and open circuit all current sources. So your circuit is like this. We have to short circuit the voltage sources and open circuit the current sources. First we will short circuit this voltage source. We remove the battery, then we will short circuit this portion. Next, we have to open circuit the current source. See, now our figure becomes like this. Between the terminals A and B is the Thevenin's equivalent resistance RTH. See, this voltage source is short circuited and this current source is open circuited. So the Thevenin's equivalent resistance is here. These two resistances are in series. Therefore, the total resistance becomes 1 plus 1, 2, which is in parallel with this 4 ohm resistance. That is equal to 2 into 4 divided by 2 plus 4, which gives 1.33 ohm. So this is RTH. Next, Thevenin's equivalent voltage VTH is to be found out. In the beginning, we studied that for finding voltage across RL or current through RL, we can use any method such as Ohm's law, voltage divider method, KVL, KCL, mesh or nodal analysis. In this case, we will apply nodal analysis. For applying nodal analysis, we have to mark the principal nodes. See here, this battery, this current source and this resistance are meeting. We will mark somewhere as one principal node, here another principal node, and here another principal node. Out of these, we have to mark one as a reference node. See, let this is our reference node and we will ground it. So voltage here is 0 and let this principal node is V1 and let this is V2. Next, we will mark the currents. As battery is connected in this way, current will be flowing in this direction towards this node, and this current source is also in this direction. So here also current is towards this node, while as this is resistive, we will mark the current going away from the node. At V2 in this branch, let current is going away from this node, and in this resistive branch also current is going away from this node. Let this is I1, this is I2, this is I3. Here this is I3 and let this is I4. Then at node 1, this I1 and I2 are coming towards the node, while I3 is going away from this node. As per Kirchhoff's current law, currents coming towards a junction is equal to current going away from this junction. That is, in this case, as per Kirchhoff's current law, I1 and I2 are entering the node, which is equal to I3, which is leaving the node. Here I2 already it is given as 4 ampere. I2 is equal to 4 ampere. I1 is equal to 10 minus V1, as the direction of current is in this way. I is equal to V by R. So I1 is equal to 10 minus V1, the voltage, divided by the resistance, which is 1 ohm. And I3 is equal to voltage by resistance, that is V1 minus V2 is the voltage divided by 1. This is as per Ohm's law. Applying these values of current in this equation, 10 minus V1 plus I2, that is 4 ampere, is equal to this V1 minus V2. Simplifying this equation, we will get 2V1 minus V2 is equal to 14. Let this is equation 1. Then at node 2, as per Kirchhoff's current law KCL, here I3 and I4 both are going away from this node, and now current is coming. So I3 plus I4 is equal to 0. I3 plus I4 is equal to 0. I3 is this V2 minus V1 divided by 1 ohm. So this can be written as I3 V2 minus V1 divided by 1 plus I4 is V2 minus 0 divided by 4 ohm. That is V2 divided by 4. There is no incoming currents, so this is 0. Simplifying this equation, we will get 5 V2 minus 4 V1 is equal to 0. Let this is equation number 2. Solving equations 1 and 2, we will get V2 is equal to 9.33 volt. See here, V2 is the voltage across this 4 ohm resistance. This voltage V2, which we got as 9.33, is the same voltage coming across A and B, that is VTH. So this is equal to VTH. Therefore, VTH is equal to 9.33 volt and RTH we got as 1.33 ohm. Now, using these two, we can draw the Thevenin's equivalent circuit. Here VTH is 9.33 volt and RTH is 1.33 ohm. Our load resistance is equal to 5 ohm. See here, as RTH and RL are in series, the same current IL is flowing through both resistances. I is equal to V by R, therefore IL is equal to VTH divided by RTH plus RL, that is equal to 9.33 divided by 1.33 plus 5. This is equal to 9.33 divided by 6.33, which is equal to 1.47 ampere. I think this class also might have been useful to you. If you found any difficulty in understanding any terms used in this class, you can refer to my previous classes, the links of which are given below. Thanks for watching. Please like it, share it and subscribe it by pressing the bell button so that you will be getting all the notifications of my future videos also. See you next time. Bye.